Today, we're talking about advanced ixml. I was asked to do a short introduction to ixml to start off with, so non-advanced, for people who didn't know what ixml was so that they could quickly get up to speed. So that is what I'm going to do. So this link, cwi.nl/Stephen ixml advanced is where the tutorial is, but the first bit doesn't use that. I think there's more material there than for 3 hours, but that doesn't matter because it's designed for self-study as well, so that we can do some stuff today, and then if you want to carry on with the other stuff, then that's fine. So this is the second tutorial. There's an introductory tutorial as well. They're both hands-on, which means that I talk for a bit and then you do some work. In this case, I talk for a bit longer and you work for a bit longer, but the ideas are the same. All the exercises have answers at the back, so you can look at them. I do go over some of the exercises, but not all of them. Actually, if you go to the tutorial, it says there are 3 implementations. One of them is my own one, but my server died, and I haven't re-established it yet. So you've got 2, but they're both very good. So and they work in the browser. So you can choose them. They're both very, very similar. All right. So this is the quick introduction. Textual documents have an implicit structure that we as humans can look at the thing and see that structure. But computers need to know more about the structure, which is why we have markup languages, why there's XML or SGML to actually make that structure explicit. Invisible XML works differently by you describing the format of the document, and then ixml adds the markup for you. So for instance, a date, to take a very simple example, we can recognize the day, the month, and the year there, but we have to describe that. So we say a date is a day, a space, a month, a space, and a year. A day is a digit followed by an optional second digit. A month is then the 12 months. The ... is not ixml, but you just imagine all of them filled in there. The year is exactly 4 digits, and a digit is any character in the range 0 to 9. So if we feed that date through that through ixml using this grammar, then we get something that looks like this. Now, what you could see is absolutely everything is marked up in the XML, including the digits. But we're not really interested in the digits there. So what we could do is add a minus before the digit, and what happens then is that digit doesn't appear in the markup. So just to go back there, you can see the difference is that by putting a minus in front of the digit, then all the numbers just appear directly in its within its parent element. So let's add another format to that now. So also with slashes, 5/11/2025. So a date is now either date, month, and year, or day / numeric month / year. And a numeric month is just like a day, an option 1 or 2 digits. And if we process 5/11/2025, then we get day, month, and year. And what you can see is the slashes are still in the output because everything ends up in the output. All that gets added are tags around the structure. So this is a new feature that's been added to all implementations. It will be added to the standards, but it's not in the official standard yet. And that is that allows you to rename a rule on serialization. So whereas here you'll see we've got day, numeric month, and year, here it says that a numeric month gets renamed to month on serialization. And so then our output then says day, month, year. If you want to express several dates, then you could just say date plus. But the thing is that that doesn't allow you to have any spaces between them. So you can, for instance, better have a grouping of a date followed by some number of spaces and then repeated, so 1 or more of them. Or you could say dates, and this is the separation, the plus. It says it's a number of dates separated by a comma and a space. So the first one allows spaces after the date, after the last date, and this second one only allows comma space between dates. And because we've got two formats of dates, then, for instance, you can mix the two formats with commas between them, as in this last example. Attributes, you could say that any rule is used as an attribute, and then that attribute turns up on the parent element. So for instance, if in this case I've turned day, month, numeric month, and year all into attributes by putting an at the front, then if we've got our input, we get 5/11/2025 gives you the date, and then with 3 attributes. And here you can now see those slashes very visibly, because of course those slashes end up nowhere except in the body of date. And if we want to get rid of those as well, then we can add minuses before the spaces and the slashes, and then you get an empty element. So we've gone from this to this by deleting the spaces and slashes in the input. Ambiguity. So a grammar can be ambiguous, and an input can be ambiguous. So if we take an example, here we've got dates in two formats, the US format and the world format. The US format has month/day/year, and the world format has day/month/year. Now, in many cases, it's unambiguous, as for instance, the 31/12/2025 is unambiguous and will appear as a world date, and 12/31/2025 is also unambiguous, and so would turn up as a US date. However, 5/11/2025 is ambiguous. We don't know which one is a month, and ixml will say that. It will say, well, this is from my implementation, so this is the format of the ambiguous information you get. It says the input from line .pos 1.1 to 1.11 can be interpreted as date in two different ways, either as US or as world. And then you get this on the top level element of the output, you get this extra attribute, ixml state equals ambiguous, that tells you that the input was ambiguous. And so this is just one of the interpretations that's possible. So just to recap the format, so I'm nearly at the end of my introduction, which is good timing. So the format is a rule consists of a number of alternatives separated by semicolons and then terminated with a full stop. The elements of an alternative can be a non-terminal or a terminal, for instance, strings with quotes around them. Terminals match a literal string, and they can either be strings like that, and you can get the quote symbol that's around it. You can, if you double it inside, then you just get one of them. You can do encoded characters, which are just Unicode code points. Those and then character sets which match a single character and consist of strings and encoded things and ranges, so like A to Z. Something that I haven't demonstrated in the examples before, but you can insert characters in the serialization, in the output, and that's going to be used in the first exercise. So plus string doesn't match anything on the input, but it turns up in the output at that point. You can group things. So you've got alternatives between brackets, and you can have options, which is a question mark either after either a terminal or a non-terminal. Repetitions, 0 or more is A star, 1 or more is A plus, and then the separators which you saw, A star star B and A plus plus B. You only saw minus, which means do not include in the serialization. If it's a terminal, then it doesn't appear at all. If it's a non-terminal, then you don't get tags for it. At for serializing a non-terminal, but only works with non-terminals as an attribute. And you hardly ever need to use it, but in case you need to override the default, then cap does serialize it in the serialization. but that's default, so you hardly ever need to use it.
What's the exception there, by the way? Why would you need to use it?
Well, so so for instance, in digit, I had minus digit so that it didn't come with tags on it. But in one of its uses, if I did want it to have tags, then I could put the cap before it. So I could say cap digit in an alternative, and that in that case it overrides the default, which is the minus on the rule. Yeah, yeah, yeah. Okay, so just to get you off the ground, and we've got a small example here. It's dates again, but in Finnish dates are written differently, 21 dot and then these names. And so I want you to write a piece of XML to read Finnish dates and serialize them as 21/9/2023, for instance. And that's where you use insertions. So what you're going to do is delete the input name, for instance, what was it, Siskuta, and insert the number, the equivalent number. So if you click on the tutorial, so let me go back where I said follow along. If you click on there, you can just copy and paste the texts so that you don't have to type all those names out. All right. Okay, so we're going to carry on. So this is what is available to do, which I don't think we'll do in the whole time, but at least at the end there are case studies of particular grammars, which we may not get to, but I will try and do all the other stuff, and then the case studies you can look at home if you want. So as I said, all characters in the input by default end up as character content in the output. The full grammars are in the tutorial in front of you. But for instance, if I have I colon equals 0, and I've defined a rule, assignment is an identifier, colon equals, and an expression, and then with the necessary rules for expressions, then you might get something like statement, assignment, ID, and that's the I, and then the colon equals, and then the expression, which consists of just a number. So, and as I've already said, effectively all ixml is doing is putting tags around parts of the input to expose its structure. So the nice thing about this is that there are some advantages to this approach. You lose no information. The output contains every single character of the input. And in fact, to get your input back, all you have to do is concat the character content. In fact, in a browser that has no style sheets, then it might just give you just exactly the input. One option is to delete terminals that don't add any information. That is, that only add structural information, but don't add any semantic information. So in the example that I just showed you, an assignment, we now know it's an assignment, and that's because it had a colon equals in it. So we can delete that colon equals in the serialization, so that then we get the only information characters, which are I and 0, which are which is semantic information and not structural information. Another option is to put all your meaningful characters into attributes. And in fact, if you look at the ixml grammar for ixml, you see that that's what we do. All the meaningful characters end up in attributes, and all other characters deleted. That means that you actually have no character content in your XML at all, only elements. One of the advantages of this is that you don't have to fight with the XML whitespace rules, and so it's much easier to pretty print your XML as a result. So in this case, here we've got an assignment. We've deleted colon equals as a not meaningful, I mean only a structural element, and then we put our names and our values into attributes. So then we get the assignment is an ID with an attribute name equals and a number value equals 0. The only thing you have to watch out for this is that you can't have more than one attribute of a given name. You can have, of course, more than one element of a given name, but not more than one attribute. So that might limit you in using this this technique. Something to watch out when you define attributes is that they lose structure. That is to say, your grammar specifies a structure to a thing, but if you specify that a non-terminal is to be serialized as an attribute, then all the terminal characters of that get concatenated together as a single thing. So, for instance, if we had a grammar for URIs, so for instance, we've parsed this as http www.w3.org/2002/xforms. If we said IRI is now to be an attribute, then because we've deleted the slashes in between, then it just gets turned into an amalgam of all those letters. So that means that you have to watch out if you decide to define something as an attribute, not to delete the structured characters like slash, because the structure will be lost in the attribute. Yeah, so in that case, you don't delete the non-essential terminals, the structural terminals. You have to keep them. So it may not matter that the structure has been lost. One thing you have got is that you've parsed it and you've checked that it's a real IRI, that it's properly formed, and it depends what you want to be doing with the result. It does mean that it'll have to be parsed again. So in that case, it might be better to retain the structure, but it's up to you how you're going to use the resulting XML. Something to be aware of, it's that the marks on the contained non-terminals are ignored when you're combining non-terminals into an attribute. That is, they have no effect because all that gets concatenated are the non-deleted terminals of the children of that node. Now, so you've seen minus being used for stopping elements being getting their tags, and the question is, where should you put that? Should you put it on the rule, or should you put it on the use of the rule? And the answer really is that it's best to make the default whatever the default should be. So if the default is never to have tags, then to put it on the rule, such as this minus subtype. But if the default is normally to have the tags, then to put the minus on the places where you don't want them, that is where you use them. So the good practice is put the default on the rule and override it at use. The nice thing about that is that you can see at a glance by looking down the left-hand side of your grammar which rules are going to have tags and which ones aren't in the default case. Yeah, you could mark both the rule and its use, but that makes it harder if you decide to make any changes. So my advice is to put the default on the rule and put the overrides in the usage. If a rule is marked as deleted or as an attribute, you can override that with cap, and cap then makes it into an element with tags. So the definition here says minus subtype, which means don't add any tags to it. But then in this usage here, subtype has got a cap on it. And so that means now in that case, include it as a sub-element. I hardly ever use cap. It's hardly ever needed, I would say, simply because it's the default. But it's good to know that it exists. All right, here is your next exercise. Wikipedia has a markup language for pages that includes the following notation for links. So 2 square brackets, the link, and then the text with a bar between it, and then 2 closed square brackets. And it produces a result like an HTML element, href equals, so it's added /wiki/ before the word link, and then it puts the text content in the element. So write some ixml to do that. So this is what the answer should approximately look like. We want to produce an A element, so it's got to be called A, right?
Yeah.
We want an A at the end of it. So it starts off with two open brackets, except we don't want those on the output, so we put a minus in front of it. It's followed by something that's going to be called href, because it's going to be an attribute called href, and then the bar, and then our content, some text or whatever we want to call it there, and then the two closing brackets, except we don't want this in the output and we don't want this in the output. All right. Now, what does an href look like? Well, it's an attribute. So we've got an A element with an href. What's an href look like? It's just a bunch of characters, but we have to add /wiki/ before it, because that gets added by Wikipedia. So we add that, and then what do we want? Well, we want allow any character that isn't a bar, because it ends with a bar. So how do we do that? We say the complement of bar. We'll do a plus there. Thank you. We want more than one of them. Thank you. Exactly right. And what does our text look like? Well, it's the same thing, except we don't want it as an element. So, and then it's just any character that isn't a close bar plus. So there are three usages of non-terminals, you could say. There are those that represent real semantic elements that are there so that you understand what the content is. So for instance, like statement, assignment, ID, expression, and so on. Those that are there only to enforce structural requirements, but once those requirements are achieved, further play no role in the output. You're not interested in seeing them in the output. They are only there to make sure that the structure was correct. And those that I call refinements, that are only there for convenience, where you give a name to something just because you're going to use that several times, but doesn't necessarily reflect structural or semantic requirements. So what I'm going to do now is to show all three in action by taking a simple arithmetic expressions and writing a grammar for that. We're only going to have addition, multiplication, and bracketing, and only numbers and identifiers. So this is an example of recognizing operators and operands, but not necessarily structurally. So in this case, plus and times are at the same level, so that a times doesn't happen before a plus, in other words. So this is a very simple expression. It says it's just a repetition of operands separated by operators. In this case, the operators are plus and times, and operands are either an ID, an identifier, a number, or a bracketed expression. An identifier is letters. This L comes from Unicode. So Unicode characters are classified within Unicode as certain cases, and capital L is anything that counts as a letter. So the nice thing about this is that you don't have to know what letters there are in the world. This will work for Chinese and French and English and Dutch as well. So that's supplied by Unicode. There are a number of properties. So you can say L and then a lowercase u for uppercase letters, and lowercase l for lowercase letters, and so on. A number is the range from 0 to 9. So operand is here what I would call a refinement. It gathers the three types of operands together, but you don't really necessarily care about them. So if we say A plus 2 times B, then we get just expression, operand, operator, operand, operator, operand, just because we're saying it's a list of operands and operators. Clearly, we can delete the operand tags so that then we just get expression id, operator number, operator id in a simple way. You don't have to have the word operand anymore because a number is clearly already an operand. The operator element, on the other hand, serves a necessary purpose because if you took it away, then you'd just be left with characters again. You've lost the semantics of it. Now, let's talk about structure. At a semantic level, multiplication has to be done before addition. So we add some structural elements, and traditionally this is how it's done. Expression is a sum. A sum is either an expression plus a product or a product, and a product is either a product times an operand or an operand. So that means that operands are pluses, are products, which means that multiplications get done first. So for A plus 2 times B, then we get a structure like this. We're going to fix it up in a bit to make it more useful. But what you can see now is that we've created a semantic element called sum that has two operands as children. So in this case, the top level sum has an expression and a product as its children. So we've now got the right structure, but we've added several layers of elements that don't really add anything to the understanding. And that's where we can now delete some of these sub elements so that we still have the right structure, but we don't have to view the elements that created those structures. Ideally, you see, we want to have expression is a sum of ID and a product of a number and an identifier. So getting rid of all those excess elements, we have to redefine it. So we only want a sum element, for instance, if there's only an actual plus involved, and we only want a product element if there is a times involved. Now, I should say that programming languages typically define their expressions in this way because they don't care about the fact that it's got all these extra elements in between. So if you look at many programming languages, you'll see definitions like this because it gives you the right structure, and they don't care about those extra elements because they're not looking at elements, they're just telling you what the structure is. But we want to have a structure like this because we do care about the output we get, and so that's why we're going to redefine it differently to how a programming language traditionally defines it. So what we do in the rule for sum, it may be that the operand of plus is not a product. So what we're going to do is introduce a term and say that a sum is an expression plus a term, and that a term is either a product or an operand. So there we've taken, we've split the right-hand operand of a plus into two possibilities, either a product or directly an operand. So that means that we now also have to add term at the top level to expression, which was originally just a sum. And so we do the same thing. A product is a term times an operand. Term is only there for structural reasons, so we don't want that as output. And so if we apply this to the example input we got an expression is a sum between an ID and a product, which is a number and an identifier. So the whole grammar now looks like at the bottom there is an expression is a sum or a term. A sum is an expression plus a term. A term is either a product or an operand. A product is a term times an operand, and an operand is an identifier, a number, or a bracketed expression. So the last observation is that within a bracketed sub-expression like A times 2 plus B, we get the expression element in the middle, and we don't need that anymore. And so in the rule for operand, we say that expression doesn't produce tags around it. And that with that result, we get what we were trying to achieve in the first place. So your exercise is to click on the grammar there, delete unwanted terms, and add a rule for comparison that takes two expressions and compares them with the operators less than, equal, greater than, not equal, less than or equal, and greater than equal. And all the characters are in there, so you can just copy and paste. So now I'm going to talk about attributes. So imagine a programming language with type declarations that look like type pointed to integer is called refint. Now, we could write an ixml grammar that included this. So here we go. Type declaration is type, so the string type with a space, and then a type, and then a colon, and then a name. And then I define what a type is, including pointers and names. And a pointer is, for instance, pointer to, and a subtype is a name, and a name is just some letters. So if you that top line, if you put that through that grammar, then you'd get a structure like this: type declaration with a type, and at the bottom a name refint. So if we made the name of the type in the type declaration an attribute, so therefore I put an at in front of the name, then all of a sudden that refint appears at the top. So what you see is that the name has ended up earlier in the serialization than the type it defines. So even though that refint was after the type in the definition, it's now ended up before the type in the serialization because it's been moved up to an attribute right at the front. So this is the only place in ixml where reordering happens. So in other words, all elements come out in the same order that they come in, as it were, except for attributes that end up in front of the place where they're defined. But this can be useful. So to go back to the example that we just had with comparisons, for instance, if you had a less than equal 0 with using elements, then you'd have the compare operation in the middle there. But if you turn that into an attribute, then you would get a comparison with the operator right at the top in the front, and then it's two operands. So that can make later processing easier. There's some interesting things that happen with attributes that you have to be aware of. So if, for instance, in this case we got a subtype, a name, if we change name now there into an attribute, we would get this. So just go back. So you can see that it moves up. The subtype is just a name, but we make it an attribute, so we get subtype name equals. But if we then delete subtype by putting a minus in front of it, then what you see is that the name moves up one level because the attribute has to move up in the tree, and so it moves up to the first parent that hasn't been deleted. So let me just go back here again. So we make the name into an attribute, it turns on the subtype, but then I delete the subtype, I put a minus in front of it, and so the name then moves up one level, because an attribute has to go on an element, and it has to be a parent element of where higher up in the hierarchy. So it ends up quite high, in other words. So so that's an important thing to bear in mind, that attributes appear on the first non-deleted element above it. Okay, so what you're doing is taking the earlier grammar for expressions, and if you didn't finish it, then you can just go and get the example, the answer that's given at the back of the tutorial, and make the comparison operator an attribute. Then, instead of saying sum is expression plus term and product is term times operand, use repetitions, so that you say a sum is a term plus and then a list of terms separated by pluses, just to see what the difference is in what you get as a result. So you're going to change the definition of sum, but you're also going to make the comparison operator an attribute. Okay. So we're going to talk about ambiguity. And in fact, I would say that when learning ixml, ambiguity is going to be your biggest bugbear, and the reason is because your eye doesn't see that it's ambiguous, and the parser sees that it's ambiguous, and then you've got to work out what it is, how it is that it's ambiguous, what you've done wrong, and so that's it's something you really need to get used to. So you will regularly be confronted with ambiguity, and in some cases, the content really is ambiguous. And so, for instance, that early example of a US versus a world date, it really is ambiguous because you don't know which to interpret it as. But in most cases, it will be a problem in your grammar. And you may not care as long as you get a result that looks decent. But you should know that ambiguous grammars run slower because it has to parse it in lots of different ways. And secondly, you can't be sure that the serialization you will get is the one that you intended in the first place. Now, there are lots of reasons that ambiguity can occur, and I've just listed a few of them. For instance, if you nest repeats within repeats, then and I'll give some examples of all these. Then you may get an ambiguous result. If a rule could be empty in more than one way, then you get ambiguity. If you've got spaces and you handle them inconsistently, then you get ambiguity. And if you include the termination of a repetition in the repetition, then you get ambiguity. And I'm going to treat all of these just to show you some examples of why you would get ambiguity. So, for instance, and this is sort of similar to ixml rules, but if you say that a specification is a squiggly bracket with a number of rules, and a rule is an optional definition, oh, no, sorry, a repeated definition, but 0 or more, and a definition is just an ID and a value, then an empty specification could be 0 rules or 1 rule with 0 definitions. And so you have to just fix this to say which one it is, because it could choose to say, okay, well, so it will say there are 2 interpretations of this, and I don't know whether it's an empty specification or a specification with an empty rule. And this is because we've got nested repetitions here, both of them 0 length. In a way, it's empty in there are 2 different ways that it can be empty. So you fix it by making one of them a plus, depending on what your needs are. And in this case as well, if you said a rule is a definition or a reference, and a reference is an optional identifier, then again, both sides of both parts of that rule could be empty. And so again, if it's empty, then it doesn't know which of the two it's got. My implementation does warn you in all cases where it can be empty in more than one way, and I don't know about other implementations. And another case, which is kind of, I mean, you would think that it was obvious that what was intended is for instance, if you wanted to say up to 4 digits, 1 to 4 digits is a digit followed by an optional digit, followed by an optional digit, followed by an optional digit. But the problem is, and that's the intention, but the problem is that if you've got 1, 2, 3, the parser doesn't know which of the 3 has been made optional. So it could be 1 optional 2, 3, or 1, 2 optional 3, or 1, 2, 3 optional. So you have to be specific. You have to make it unambiguous by doing it this way, essentially saying that it's a digit followed by optional 3 digits, and optional and 3 digits is a digit followed by optional 2 digits, and so on all the way down. Then it's unambiguous. And although you could do it the other way around and say an optional digit followed by, but it's better to be explicit with what you start with, because it can make decisions much earlier on. So if it sees a digit, then it knows that it's got optionally 3 digits after it. But if you said that if you said it was optional 3 digits followed by a digit, then it just makes it slower. Yeah, I'm going to treat spaces in more detail shortly, but if you have a rule, for instance, where a set is some start symbol and some numbers and an end symbol, and the start symbol is a bunch of spaces, possible spaces, and then an open bracket and a bunch of spaces, and then your numbers 0 or more separated by a semicolon, and then your end character is spaces and then a close bracket and spaces, where spaces are 0 or more spaces, then the intention is to allow optional spaces before and after that symbol. But the problem is, if you've got open bracket, space, close bracket, the system, well, the parser sees that those spaces could be following the close bracket, the open bracket, or they could be before the close bracket. And so it says, well, there are two ways that I can interpret this. So I'm going to treat this in detail shortly, but this is a case where you would get ambiguity because the spaces would match in several different ways. This is something I saw in the wild, that somebody wrote. So the input is a bunch of lines, and a line is one or more characters, but so that twiddle open bracket close bracket means a random character, any character. So it's like saying dot star in regular expressions, followed by a new line. But the problem is that that dot star matches new lines as well. So a new line could be matched in that first part or in that end part. So what happens is that if you've got input like 1, 2, 3, it was meant to be interpreted as a line with a 1, a line with a 2, and a line with a 3, but it can be interpreted in 3 different ways because it could all be 1, 2, 3 as a single line because it's matched the new lines as well. So the correct way to do it is to make sure that you exclude the terminating character in your character set. So you're saying any character except a new line repeated 0 or more times, and then your new line. It's important to note that ambiguity is a property of the input and not necessarily the output. It is possible. So for instance, if I deleted all spaces in that earlier example, then actually all serializations would be identical, but it would still be ambiguous. There would still be n numbers of possible ways of parsing it, and the system doesn't go and compare all the serializations to see if they're the same. It just says there are more serializations, there's more than one serialization, you ought to fix this. So even if the serializations would turn out identically, you will still get the report that is ambiguous. Yeah, so I've said this already. Ambiguous grammars run slower because parts of the input have to be processed several times. So this is what I said: write the rules in interpretive so it's clear which apply as early as possible. So for instance, D4, make sure that it starts with a D and that it doesn't start with an optional thing. So try to move your optional things to after and not before. You might not have that option, but if you have, then do that. It's a small point as well, but in this case, if you've got two different things that could have brackets around them, then better to make it into one rule, so that you've got the open bracket and then the decision over the expression or declaration, rather than having two alternatives. Again, it doesn't make a huge amount of difference, but it does slow your parser down because it has to run two different rules rather than just one different rule. Okay, so this is quite a tricky exercise, but an interesting one. So your input is letters and numbers, are not separated by anything, so run together. And so if you've got your input like here, A, B, C, D, E, 1, 2, 3, 4, D, E, F, G, and so on, I want you to give the output as word, number, word, number, word. And don't feel bad about it if you feel if you find it hard, because it is hard, but it's an interesting thing to think about. It's made harder if you know about regular expressions, because you expect them to work in a certain way, which grammars work differently. So that actually makes grammars more expressive than regular expressions, but it means you have to watch out that you don't think in terms of regular expression idioms. A typical mistake for the previous example is to do it like this. The problem with this definition is it allows two words to be adjacent to each other and two numbers, so that AB1, 2 could be a word and a number, or two words and a number, or a word and two numbers, or two words and two numbers. And the longer the string, the more ambiguous it becomes. And that's because we've got nested repetitions with nothing between. So here is one way of doing it, to say that the input is a word number or a number word. A word number is a word followed by a number word, and a number word is a number followed by a word number. Another way, which actually I find more charming, is to say that the input is either a bunch of words separated by numbers and then followed by an optional number, or a bunch of numbers separated by words and then followed by an optional word. And it achieves the same effect, but in a rather charming way. You could reduce it to a smaller version. So this last point, if numbers and words were separated by something, for instance, a comma, then you would be able to write it in the most obvious way, because it's the comma that divides it. But these are things that you have to be aware of, that you should not take your regular expression idioms with you, because they will trip you up. Here's a very similar example, again, that I've seen in the wild. Is input consisting a number of lines, which each line starts with some spaces, and then some content, and you're not interested in the spaces, basically. So I saw this written. So the input is a number of lines. A line is some spaces, and then it's content, and then a new line. And the content is just saying anything but the new line. So everything up to the new line. The problem is, of course, that the space star there is not greedy, and so the content also matches spaces, because space is included in that content. So in other words, you have to write it so that the spaces are eaten up completely, so the content doesn't start with a space, but then can have spaces after that. So in other words, all leading spaces get ignored, and the content doesn't start with a space, although it may contain spaces. So the first character of the content mustn't be a space, in other words. I'm not going to give you this exercise, because it's even harder, and I think you've understood the issue. But there's a useful thing to know about, is that just like the Unicode L for letter, there's also a P for punctuation, which can be useful. Okay, so now let's talk about spaces. So some formats are fixed format. Every character has to be in a certain place in the input. But others are free formats, which in particular, that means that white space can be included anywhere. And so what I'm now going to talk about is how you should approach dealing with white space, so that you don't get ambiguity like the example I gave earlier. So in the earlier example of types, I put explicit just one space, just to make it simple. But actually, we want to allow multiple spaces between the different symbols there. So this is how you would do it. So I've just defined S as a rule that accepts one or more spaces. So one or more. So I've said that you've got the word type followed by one or more spaces, and then a type, and then a colon, and then optional spaces, and then the name, and then a full stop, and then optional spaces. And for instance, a pointer followed by one or more spaces, followed by the word to, followed by one or more spaces, followed by a subtype. The advantage of this is that you can then make your set of space characters greater. So tab, carriage, return, line feed, and so on. You can add those to S, and it will still work equally well. So what you have to do is be consistent. And my advice is to put them as close as possible to the terminal. So this S thing that allows spaces as close to the possible as to the terminal, but after them, because that means that you've got the terminal and then you eat up any spaces that follow it. If you put them after non-terminals, you do risk allowing spaces to be ambiguous because the spaces might occur within the non-terminals. And if you add them before the terminals, then you slow down parsing because it doesn't know which, if several rules can start with spaces, then it doesn't know which of those rules is being selected, so it has to try them all. Normally, you don't want to retain your spaces in the output since they're normally only used for syntactic reasons to separate items. They don't hold any semantic value except in strings, for instance. Here's a technique for converting multiple spaces into a single space is by deleting, so accepting the first space and then deleting all following spaces. Or another way is to delete all the spaces and insert a single space. I'm going to carry on talking. Is that all right? So if a symbol consists of several characters, like the walrus operator, as this is called in Python, it's easy because you just put the character straight in the rule. However, it needs a little care if you're going to use a multi-character symbol to end a repetition, which is what we had in the link example, where parts of the symbol may occur in the repeated part. So if you wanted to have a single close bracket and then the double close bracket to finish the link, then you have to be careful. So I'm going to give you this exercise now straight away to let you try and address it. So in ixml, comments are a single character, squiggly brackets. So what we can say is a comment is an open squiggly bracket, and then any number of characters that aren't squiggly brackets followed by a closed squiggly bracket. Now, I could have chosen XML comments. I've chosen Pascal comments here. They're enclosed in open bracket star and star close bracket. But they are allowed to contain asterisks, just as XML is allowed to contain a single hyphen, but not a double hyphen, I think, in comments. So here is your input that I want you to write ixml for, and the output that you should get. So each line here is a comment, a single comment, except the last line, which is 2 comments after each other. The hint that I'm giving you is that there are several ways to do it, but it is possible to use a top-level rule of open bracket star content star close bracket. So the observation is that a close bracket may occur in a comment, but only if it's not preceded by star. So what we say is the content is an optional bracket and then a number of C's. And a C is either not a close bracket or not a star followed by a close bracket. So that first one you need as a limiting case. But it's the definition of C that's the important one, that it says we allow anything except a closed bracket or a closed bracket that is preceded by anything but a star. So to move on, I want to talk about how to deal with non-context-free languages, because ixml handles, in the general case, context-free languages and can't, in general, handle non-context-free languages. So to give you an example, a string of A's followed by the same number of B's is context-free, because I can say an AB is the letters AB, or the letter A followed by an AB followed by the letter B. So that will process AB, AA, BB, AAA, BB, BB, and so on to unlimited depth. However, if I said a string of A's followed by the same number of B's and then the same number of C's is not context-free, and you can't write a grammar for that. And so the only option you have is either to say, I won't count and I'll just accept a number of A's and a number of B's and a number of C's, or to explicitly restrict the depth and say, well, ABC, AA, BBB, CCC, and then you have to stop at some level. At whatever depth. So those are the only options you have for non-context free languages. Another example of a non-context free language is XML itself, because the opening tag and the closing tag have to have the same name, and there's no way you can do that in a context-free grammar. So in that case, you have to just accept there's a tag and there's a tag, and you can't check for them. You can put them both on the element if you want, but you can't actually guarantee at parse time that those two words match. Another example of the contrast between context-free and non-context-free is nested lists. So, for instance, here I've got bracketed lists, and an element of a list can be a bracketed list, and so on to any depth. Since the nesting start and end is explicitly made with brackets, it's context-free, and so you can write ixml that would process this to an unlimited depth. However, here are two real-world examples. Real-world in the sense that there's a language that's used for family trees. It says the level of nesting with a number in front of it. So these, and the other example is Python-style indentation, which is also non-context-free. That is to say, you can't check either of these two to unlimited depth, but you can to a finite depth. You could say, for instance, I'll support up to 9 levels of nesting. So there's an exercise to do this, but time is short. We've got another 4 minutes, so I won't. But you can do that at home if you want. It's important to be aware there's no implied ordering in the alternatives of a rule. And there's no equivalent of an else either. So each alternative has to be explicit in what it accepts. So in A is a B or a C or a D, that's not saying try B and then try C and then try D. No, they're all tried in parallel. And that's why you get ambiguity, because more than one of those might match. I'm going to stop here. So the tutorial is online, so if I go back to the contents here, so we almost got to the end of the general stuff, so we didn't get to designing formats, and then the rest were case studies. So thank you all.